Hello everyone. So up until now we've been focusing on Gauss's law here, but there are three other Maxwell's equations that involve magnetic fields. So we're going to get started talking about magnetic fields in this course. Let me remind you that D is equal to epsilon E, and in a similar manner, B, the magnetic flux density, is equal to mu, the permeability, times H, which is the magnetic field intensity. And it's kind of similar to D equals epsilon E, and we will definitely talk more about that. In the case of electrostatics, we actually don't care about the magnetic field, and here's why. If the charges are stationary, this J value, which is current density, is equal to 0. And if the charges are stationary, nothing is changing with respect to time, and so this term goes to 0. And so this means that your H field is equal to 0, which also means your B field is equal to 0, which is why we haven't discussed magnetic fields up until now. So in these next videos I'm going to make, we're going to be focusing on really understanding what these equations mean, the ones that have the magnetic field in them.
Hey Milan, guess what? Guess what? You got 59 likes on a video. Are you excited? Wait, no, you aren't? Why not? Oh, Milan, come on, that's silly. I mean, I know there were like over 600 views on the video. You mean you expect every single person who views that video to like the video? I, I don't know. I think you're just asking a little bit too much, Milan. Too much, okay? So needy.
But first, let's talk about what a magnetic field, or B&H, represent physically. If you recall when we talked about electric fields, what an electric field represents is the force that would be present on a charged particle if you placed it at that point. And it turns out that a very similar thing applies with magnetic fields, but it's a little bit different. It turns out that if you place a point charge at a certain point in space with a certain magnetic field value, if the charge is moving in some direction or velocity v, the force that that charged particle will experience will be out of the page, because that would be the v cross b as defined by the right-hand rule. So you'd multiply the charge q times the velocity, and then you'd cross it with b, and so it would experience a force that is out of the page or perpendicular to its velocity. We can combine the effects of both the magnetic force and the electric force, and the total QE plus QV cross B is known as the Lorentz force. So for me, this helps me kind of get a real grasp of like physically what it represents for a field to be present at a point. It's telling you about like real forces on charged particles, the real forces that they would experience if you were to place them at that point in space. All right, so now I want to take the time to step through the three other Maxwell's equations that have B in them and really try to understand what they are saying. The first one is del dot B equal to 0. You could think of this as like Gauss's law for magnetic fields. So what is this saying? It is saying, going back to our definition of divergence, it's the outward flux B dot ds per really small cube, And it's saying that that is equal to 0. That's unlike Gauss's law for electric fields, where it's equal to rho v. And so what this is telling you is that there's actually no such thing as a magnetic point charge or magnetic monopole. So you can't have a little point charge that emits a magnetic field like this. So far as we know, it doesn't exist. This doesn't exist. So in my next video, I will be discussing Ampere's law, and we will just work through each one of these equations and really try to understand what they mean.